So I always stress that when I talk about rational functions, it's just functions that look like ratios, which ratios look like fractions. The book calls it a quotient of polynomial functions, which a quotient just implies division in a fraction as well. Now, I'm going to use this notation here that you're seeing over here. The function f of x, the rational function, is equal to n of x over d of x. So what I just mean there is like the polynomial in the numerator and the polynomial in the denominator. So you're going to see me write n of x and d of x. If you prefer to use like numerator and denominator, you can replace those things if you want to. Why, as a mathematician, would I make a statement such that d of x does not equal 0? Because I can't divide by 0. Okay. So we've encountered this already in chapter 1 when we were doing rational functions and their inverses. This is going to cause a restriction to your domain. So you'll, like when you're listing domains, you'll think about what are the things that make the denominator equal 0. Let me leave those things out. Okay, basically I have 3 steps to graphing a rational function. So my first step, this one might be new to those people who are coming from the Algebra 2 track. Okay, my first step says factor n of x and d of x. And again, if you don't like n of x and d of x, you can write numerator and denominator. Back in Algebra 2, our textbook really looked at what I would call simple rational functions. So there wasn't really anything to factor in Algebra 2. But in pre-calculus, we're going to encounter some, like, see, we have quadratics there. And this is where we can encounter what's called the whole. So we want to make sure everything is factored. So we're going to talk about wholes. And I've got that function over there on the right side. We're going to keep using this function for the whole notes. I'm going to do all the different characteristics of this function. So you can kind of decide how you want to organize it. Do you want to do your notes on the left side of your paper and then do the example off on the right? Do you just want to put all the notes about rational functions and maybe on the next page do your example so you have all the examples together? Okay, that's kind of up to you how you want to organize your notes. We're going to keep using this same function over and over again. Just kind of verify with your group members that you can factor the numerator and the denominator here. Let's see if you agree on factors. I'm going to call on you, so you might want to talk to your group so that you know what the answer is. Yes, the model. That's perfect. Okay, Ryan, did you guys factor the numerator?
Yeah, you got x plus 1, x minus 1.
X plus 1, x minus 1. Excellent. That's a difference of perfect squares, so make sure you're on the lookout for that. Grace, did you guys factor the denominator?
We got
X plus 3 and x plus 1. Excellent. Okay, so we've taken care of step 1, which is factor everything. Now, what's something that you might notice right here? The x plus 1 is in the numerator and in the denominator, so we get to cross this off. And what that means, when you get a cross off a factor, because you have one in the top and one in the bottom, that means you have a hole in your graph. So let's write off to the side, what does it mean to have a hole? If n of x and d of x share a common factor, then there is a hole at the zero of the factor. Now, there will be times, like on your homework, when you factor the numerator and the denominator and nothing cancels. That just means your graph doesn't have a hole. Great, move on. Okay, but you always want to factor first. The only way you'll ever find that hole for me is if you factor. So you want to do that at the very beginning. Okay, always factor first. A hole is going to be just like what it sounds. Like you're going about your merry way, drawing a graph, and then there's like a hole, which is going to be marked as an open circle at a single point, where you have to pick up your pencil and go on the other side. Like there is no graph right there, but the rest of the graph is perfect. There's just a gap in the middle right there. So that hole happens at the zero of the factor that is common. So we would say for our hole, we could set x plus 1 equal to 0, and our hole exists at x equals negative 1. Now, the hole is just going to be a point, so in addition to finding the x-coordinate of the hole, we actually need the y-coordinate. Like, we don't know where the hole is, but it should line up with the rest of the graph. So we have the x-coordinate of the hole. To find the y-coordinate of your hole, plug x into your remaining factors. Find the y-coordinate of the hole. So we really want to like pinpoint where exactly is this hole, so it's going to line up with the rest of my graph. To figure out that place, I'm going to plug my x, which is negative 1, into the factors that are left over. So there's x minus 1 in the numerator and x plus 3 in the denominator. So I'm going to do f of negative 1. That's going to be negative 1 minus 1 over negative 1 plus 3. So negative 2 over 2. Looks like my y value is also at negative 1. So now we know on our graph, if we go left 1, down 1, we're going to make an open circle. It's a hole. It's not actually a point on our graph. The reason why we don't want to make it a closed point on our graph is because x plus 1 in the denominator would be undefined. It won't produce an answer. Okay? But it's going to be something different than the vertical asymptote we know, because the numerator is also having that same factor. You don't ever want to plug your x back into the original function. If I plugged x into like the full factors or like the original function, I'll get 0 over 0. And just so you're aware of this, 0 over 0 is weird. Mathematicians call it indeterminate. Is 0 over 0 0 or undefined? We don't know. So we don't want to plug it back into the full thing, we just use the remaining factors. And going forward, I can use this shortened version for all my other work. So I will use that factored form now. Okay? So, step 2, we found our hole. Sometimes there is no hole and you just move straight to step 2. Step 2 is identify other characteristics with your remaining factors. Now, if you don't cancel any factors, you can go back to like the original f of x, or you can use the factored form. Either one would be fine. Since I did cancel the factors, when I'm doing all these like asymptotes and intercepts, I'm going to be using my remaining factors right here just because it's less work. And I don't want to use any of the whole for the other things because it's a whole first, nothing else. Okay, so does anybody recall from Algebra 2 or Algebra 3 how you find vertical asymptotes of rational functions? So far, all classes have been And check with your group, see if anybody remembers, see if you can convince somebody that's right. How do you find the vertical asymptote? You have x minus 1 over x plus 3. Didn't groups think they figured it out? Aiden? And why not? Yeah, you'll have a major problem in this function whenever your denominator equals 0, right? Now, part of that, the x plus 1, was taken care of with the whole, but the other restriction to our domain is going to be our vertical asymptote, which is x plus 3 equals 0. So make sure you write something in your notes. Set your denominator, or d of x, equal to 0. So that'll be x plus 3 equals 0, and x equals negative 3 is your vertical asymptote. Remember, asymptotes should be written as equations of lines, so don't just say negative 3, say x equals negative 3. Okay, cool. We got our vertical asymptote. It is possible, like let's say I didn't have a whole, so I didn't cancel x plus 1. It is possible to have more than one vertical asymptote. Be aware of that. All right, horizontal asymptotes. This is something I kind of alluded to back in chapter 1 when we were doing domain and range of rational functions and their inverses. Okay, but I said, don't worry, I'll teach it to you in chapter 2. So here's what you need to know about horizontal asymptotes. And this is something some of us may need to study tonight. Compare the degrees of n of x and d of x. What do I mean in polynomial terms when I talk about a degree? What is the degree of a polynomial? Which exponent? The highest exponent. Okay, so if you need to, maybe make a little note to yourself. When you're comparing the degrees, you're comparing the highest exponent. So you compare the degrees of your numerator and denominator. And there's basically three possibilities, right, when you're comparing numbers. N of x could be less than d of x. N of x could be equal to d of x. Or n of x could be greater than d of x, right? Three possibilities. So we have three scenarios. You're responsible for all three of these on tomorrow's quiz. So make sure you know, in a given scenario, what your horizontal asymptote is going to be. If n of x is less than d of x, your horizontal asymptote is y equals 0. If n of x is equal to d of x, we say y equals a over c. This one maybe will merit writing a little something down. This is the ratio of the leading coefficients of n of x and d of x. And then if the degree of the numerator is more than the degree of the denominator, the horizontal asymptote does not exist. I'll put a little asterisk next to that one because that's the case we're going to cover tomorrow quickly. If you don't have a horizontal asymptote, it is possible that you might have a slant asymptote. Okay, so like a line, y equals mx plus b. I'm going to talk just really quickly in terms of number sense for these three rules. And I have three polynomial or three rational functions over here on the sideboard. Okay, this first one is a rational function, f of x equals 3 over x minus 2. If you compare the degree of the numerator and the denominator on this one, the degree of the numerator is 0 and the degree of the denominator is 1. So this one has a n of x less than d of x. Okay, imagine I put in a number that's really big for x. So imagine I put in 1 million. 3 over 1 million minus 2 is really close to what value? 3 over 1 million. It's very close to 0. If I cut up a Snickers bar into 1 million pieces and offer you 3 of those 1 million pieces, you are not going to be satisfied. Okay, you are getting nothing. So this is really close to 0. So as you put in bigger and bigger x's, like x's towards positive infinity or x's towards negative infinity, then it gravitates towards 0. Okay, but is it really 0? No, because it's 3 of 1 million minus 2. Okay, if the degree of the numerator and the denominator are the same, then let's say I put in 1 million for these x's, because that would be like on the far right side of my graph, right? That would be 2 million plus 1 over 1 million plus 3. I mean, essentially, isn't that like basically really close to 2 million over 1 million? Which is almost 2. But because this one has a plus 1 and this one has a plus 3, is it really equal to 2? No. So it's never really going to get to 2, but it's going to get really, really close to 2 because the number is just so big that if I had $1,002,002, it wouldn't really feel different than me having $1 million. Okay, and then the last one, if you put in 1 million, let's just think real quickly here, 1 million squared over 1 million, this number just is going crazy big. So it doesn't matter what you put in, it just keeps going bigger and bigger. It doesn't approach anything, okay, even if I'm dividing by 1 million. So that's the number sense for horizontal asymptotes. Okay, last thing is intercepts. So, oh, I didn't find the horizontal asymptote for mine, did I? Let's go back up there. Compare your degrees of the leftover factors. They are equal, right? N of x equals d of x. So the horizontal asymptote is going to be at the ratio of my leading coefficients. The leading coefficients here are 1s. Okay, so 1 over 1, my horizontal asymptote is at y equals 1. So I'll write that down over here. In my example, n of x is equal to d of x. So y equals a over c, which is 1 over 1. Y equals 1. Okay, intercepts. It doesn't matter who your math teacher is, what math class you're in, what function, chapter, whatever, the rules are always the same. If you want a y-intercept, set x equal to 0. If you want an x-intercept, set y equal to 0. Okay. Now, I can use my reduced factors. So if I want to do the y-intercept, I could do f of 0 is, what do I have, 0 minus 1 over 0 plus 3? So negative 1/3. Remember, the y-intercept is a point, so I want to write it as an ordered pair. I put in 0 for x, and I'm getting out negative 1/3 for y. So that would look like 0, negative 1/3. It's okay that it's a fraction. You're going to get some fraction numbers with rational functions because they look like fractions. So you can plot that. And then for x-intercept, set y equal to 0. So I'm going to say 0 equals x minus 1 over x plus 3. There's different ways to go about solving this one, but probably a lot of people would say, I want to get rid of the x plus 3 in the denominator, so let me multiply both sides by x plus 3. Well, what happens over here on the left side every time? It's always 0. So if you're solving a rational function for the x-intercept, there is, like, you are setting y equal to 0 every single time. There is what I would call a shortcut, and that's set your numerator equal to 0. If you think about fractions, the only way a fraction will ever equal 0 is if the numerator is equal to 0. Thank you. So set your numerator equal to 0 and you're done. You don't really care what the denominator is. So we've got an x-intercept at x equals 1, which I should write as 1 comma 0. Now, I say get the x and y intercepts because they're really fast to find, and they're going to be extra points on your graph. So you're going to be graphing, and you're going to need points, and those are easy ones to find. Okay, any questions on asymptotes or intercepts? Okay, last step, step 3. We're going to graph. Make a table of values for additional points. Now that's really like a sometimes needed thing. So every now and then your stuff that you did on the previous slide, your whole, your asymptotes, your points, your x and y intercepts, there's enough points and data there for you to figure out what your graph is doing. If you don't have enough points to know exactly where your graph is, then just make a quick table of values, pick some x's that you need, and figure out what's happening with your graph. So I took all of our stuff that we did on the previous slides and I wrote it off to the side right here. Okay, here's all the things we found for this function. I'm going to plot them first and see if I need any extra points. So I'm probably going to go like 5 on each side. Making little coordinates of planes is like zen for me. So relaxing. Don't you guys love it, making your own little coordinate planes? I know. I don't know why you guys hate it so much. Thank you, Lawrence. Okay. I'm going to plot a hole at -1, -1. How will I mark the hole? As an open circle. Left 1, down 1. Please make your open circle large enough that I can tell it's open. If you make it tiny, it looks closed. Alright. Vertical asymptote. X equals -3. Horizontal asymptote. Y equals 1. Y-intercept, 0, -1/3. So that's somewhere in between 0 and -1. I'll never know if Cade really plotted his point at -1/3 or -1/2, and I don't really care. It just should look like it's in between 0 and -1. So don't stress about a fraction. And then my x-intercept is at 1, 0. That one's easy. So I just plotted all the information I found. Well, there's a lot of really good information right there. I think I kind of know what's happening in that bottom right section of my graph, right? I've got 3 points kind of in a row. And it's not going to be a line. It's going to be some kind of curve, but it's also restricted by these asymptotes. So I'm thinking it's coming up and stays under the horizontal asymptote, and then comes down, drops next to my vertical asymptote. Okay. How many people have a guess of where the other branch is? Another part of your graph. Yeah, most people are probably going to say, like, note that this is not the only part, that we don't have any. We never found any x's on the other side of the vertical asymptote. So most people of us are going to guess that it's up here. I will warn you that with rational functions, there's all different types of rational functions, what their graphs could look like. So it is possible to get one down here, a branch. So if you don't really have a point telling you where it is, that's when you need to make that additional table of values. So like I really just need a point on the left side of my vertical asymptote so that I can verify where my branch will be. But then I'm going to guess it's stuck in between the asymptotes as well. So I'm going to pick a point, let's say the vertical asymptote is at -3, so I'll do -4. You do -4, -5, you pick -10, it doesn't really matter. You're going to do this no calculator. So I would plug it into like the reduced function and just like write out what the fraction is and figure out if I can simplify it at all. -4 minus 1 is -5. -4 plus 3 is -1. So that is just a +5, right? Now, if it comes out to be a fraction like 5/2, you still know where to plot that, right? 2.5? Somewhere in between 2 and 3? So don't stress if those come out to be fractions. They won't always be nice numbers. Let's go left 4 and up 5. And that kind of confirms what I would guess the majority of you thought for your other branch. But I do want to warn you, don't always assume you know what the rest of the graph is doing. You probably need to pick a point over there to confirm it. And then also beware, don't forget about other sides of vertical asymptotes. If you've never checked an x over left of -3, that doesn't mean that there isn't anything over there. You just haven't found it. Okay, so you need to have a graph in all the sections, all the areas. Okay, last thing, domain and range. Now, domain, you can think about two ways. You can look at it on the graph, or you can look at your function and just look at your denominator. What two values made my denominator equal 0? -1 and -3. So I have to exclude both of those. You should, when you're doing your interval notation for the domain, you should do them in order. So like, which one do you exclude first? -3 is less. So you're going to start at -infinity, you're going to come up to -3, exclude my vertical asymptote, and then I'm good from -3 to my hole, but then there is no graph right there at the hole. So I got to exclude the x-coordinate of my hole, the -1, and then I pick back up and I'm golden for the rest of my function. So what I'm excluding there, okay, I excluded my vertical asymptote and I excluded the x-coordinate of my hole. What are you going to exclude for your range? 1, your horizontal asymptote, and in this case also -1, because at that line -1 there's a hole, and because our branch was above the asymptote, not next to it, there is no graph at y equals -1. If we had the branch down below, we wouldn't have to exclude the y-coordinate of the hole. Okay, but here we will. So range, first I'm going to exclude the -1, then I'm going to come up to 1 and exclude the 1. Okay, so in this one I'm excluding the y-coordinate of the hole and the HA. Now, of course, if you don't have a hole, you don't have to exclude any coordinates for that. Okay, so sometimes there aren't holes. You could have no holes, but you could have 2 vertical asymptotes, then you're still excluding 2 numbers. Okay, it really just depends on the function, what the graph looks like. Okay, my domain and range was all down there. Does anybody have any questions about what happened here? Okay, your homework assignment is on your gold sheet. Really important that you, take, 7 problems? You take some time this evening to try some of those, even if you can't do all 7. That you do a couple of those problems, you run through the different steps. Step 1, find the hole. Step 2, find the asymptotes and intercepts. Step 3, graph. And remember, there isn't always everything. Like you can have no hole, or you could have no horizontal asymptote if the degree of the numerator is greater than the degree of the denominator. It just is what the function tells you. When you're not sure what it looks like, plot more points. Just make a little table of values. Okay. So you'll be graphing a rational function on your quiz tomorrow and a polynomial function on your quiz tomorrow. So make sure you practice both of those.